Welcome back to one more episode of our deep learning web series, a comprehensive and intuitive introduction to deep learning. In this episode, which is season 2, episode 3, I will be talking about a new type of a neural network architecture called a recurrent neural network. A recurrent neural network is very different than the neural networks that we have studied so far. Let's see what recurrent neural networks do, why they are used, and how we architect one of those, and for which use cases we will select a RNN. Before we get into all of those things, what if I told you that we have been using a recurrent neural network, maybe unbeknownst to us, all the way back from 2016 onwards, in some of the very popular SaaS products that we have been used to? For example, in 2018, Gmail introduced this really cool feature called Smart Compose. And what Smart Compose did is that it allowed us to start typing in an email and it would essentially detect what would be the most relevant text that it can autofill to complete that sentence that we are typing into our Gmail composer. And it was not autocomplete like the way we see it in phones, but it's actually very contextual, and it was very good in predicting not just the next word but the next series of words. And this was built on top of a recurrent neural network. In 2016, we saw Apple release Siri with smart features where it could essentially transcribe things that have been spoken into written text. And it also showed us this keyboard autocompletes, which are very, very smart. And that was also built on top of a type of recurrent neural network called LSTM. Now, in 2017, Facebook announced that no, in their website, they were doing about 4.5 billion translations from one language to the other. Obviously, Facebook has billions of customers from all over the world, and they all speak different languages. So, Facebook essentially built a translation tool, and that they built on top of using an RNN, a form of an RNN or a recurrent neural network. And this was doing about 4.5 billion translations all the way back in 2017. And now it's much more than that. And finally, if you look at the non-text based interfaces, PayPal announced in 2018 that they have been able to use recurrent neural networks to detect fraud in several of the transactions that they see on their platform. So, what's so unique about RNN that it enables companies like Google, Apple, Facebook, and PayPal to take modalities like speech and text and even numbers and use this neural network architecture to solve some really useful problems and create some really compelling features in their products? To understand that, we actually have to understand what is the limitation of the neural networks that we have seen so far, the neural network architectures that we have seen so far. So let's first understand that, and then we'll be able to get into what is an RNN and how does it solve these problems that are there in the neural network architectures that we have seen so far. So far we have seen a neural network architecture that is called as a feed forward network. It's abbreviated to FFN. And a feed forward network, just as a quick recap, looks like this. You have your input neurons at the first layer, which is called the input layer. And you select the number of neurons in your input layer based on the number of features on which you'd like to build a model to make a prediction. For example, you can see here that I'm trying to predict the price of a house given these four input features. The four input features are square footage of the house, the number of bedrooms it has, the lot size on which that house is, and the year it was built in. And based on these four, I'm predicting the price of the house. And for that, I'm going to train it based on some data that I've actually observed, that I've collected over a period of time. And the number of features that you see essentially become the number of neurons that you feed into your neural network. And the final output layer, in this case, because you're trying to predict only one thing, which is the price of the house, you have one neuron. We have studied this in all of season 1. If you want to go back and recap, then I would encourage you to look at episode 2 of season 1. But anyway, then you have in between this input layer and output layer, you have one or more what they call as hidden layers, and you can have any number of neurons within those hidden layers. I will not go into the details in this episode because we have covered that quite exhaustively in season 1. Anyway, so this is called as a feed forward network. Why is it called a feed forward network? Because you're essentially feeding the input here and you're trying to make a prediction at the output here. And what is happening is that the data just goes in one direction, where you go from the input layer through the hidden layers to the final layer. Okay. Now, once it gets to the final layer, we already studied this in season one. You pass it through an output function. You select the output function based on the use case you're solving. For example, in this case, you're trying to predict the price of a house. So you'd use a linear output function. If you're doing a classification problem, depending on the type of classification problem, you might choose sigmoid or softmax. But regardless of it, you'll use an output function, make a prediction. If your prediction during training is off from the ground truth value, then you would use a loss function. Like, for example, in regression problems, you would use a mean square loss function. In classification, you would use a cross entropy loss function, and you would collect that loss, and then you would propagate that loss back. So this is what we have studied so far in terms of a neural network architecture. It's called a feed-forward neural network. Let's understand this from a pseudocode perspective. So here I show you that first you're building a feed-forward neural network. I showed you how to do that in season one, so I'll not repeat it here. Then across multiple training runs, which we call as epochs, we take in a loop, we take each of the samples in our training sample sets, extract the input features on we'd like to make a prediction. In this case, the square footage, bedrooms, lot size, and year built are our input features. Then the ground truth value that will allow us to compare our prediction with what is supposed to be the actual value. You run it through the training phase of the feed forward network. You make a prediction, run it through the loss function, get the loss, and then back propagate that loss to adjust the weights. And then you run that across multiple training runs across all the samples in your training data set. There's one key observation to be made here. And the key observation is that in a feed forward network, there is no concept of a sequence. And what I mean by that is when it sees a single training sample, it basically treats that in its entirety. It does not really see that, okay, there is some kind of a sequence within that training sample, and there is no ordering in which those elements appear, or that elements of the training sample appear. Now, this is fine for data like this, where I know there is no ordering between, let's say, square footage, bedrooms, lot size, and year built, and so on. But there is some type of data where that ordering matters. Text obviously is one, because text is basically a single sentence. If that is your training sample input, is essentially a sequence of words, and the ordering of those words matter. We'll see that shortly. But even when it comes to numbers, there are certain types of data which are numeric in nature where this ordering matters. Let's try to understand that first. And essentially, if you think about it, that is a limitation of feed forward networks that we need to solve. So let's start with text. In text, the ordering of the words matter. So let's say that you're trying to build a neural network that is predicting the next word in a sentence. And I give you two sentences. In the first sentence, I say, they set the table with. And a well trained neural network should predict something like plates. Now, if I change the last word in my training sample set from with to for, and I say they set the table for, you don't want the neural network to predict plates, because that is wrong. Essentially, it might predict something like this: set the table for two. So, as you can see, even though the remaining inputs within the same sentence remain the same, just the previous token is influencing what comes next. Now, I'll give you another example. It's not just about the proximity of the word itself. So let's take an example and understand that. Let's take this sentence. She alone finished the task. So here the word alone, which I'm highlighting, is the second word in my sentence. Now let me give you another sentence. She finished the task alone. Now clearly, as a human, we have been trained on multiple sentences throughout our life, and we understand that both these sentences essentially mean completely different things. Although both the sentences have the exact same words, with just one word moving from the second position to the last position, the meaning completely changes. So, this actually illustrates that when it comes to text, it is actually important that we understand, acknowledge, and process the ordering of words that appear in a sentence if you want to train your neural network to do the right things, to make the right predictions. This also extends to numbers. So, here is one example that can illustrate this point. So, let's say I'm measuring the performance of a Java based application. And in a Java based application, the performance of that application goes down. Let's say it's a database type of an application, the queries per second go down. And you observe what's happening in your system across different metrics. And let's say the metrics are the memory consumed by the Java application, the frequency at which the garbage collection is happening, the CPU utilization of the machine on which it's running, the pause, the number of seconds or milliseconds that the garbage collection has paused, and the latency that the application is seeing. Now, when you look at it, what happens is that okay, the performance of your application has gone down, but there is a causal relationship that essentially says why it went down. Correct? For example, let's start from the top here. Let's say that the memory consumption for your JVM based application is sitting between, let's say, 10 and 50 megabytes. And then at some time period, that memory starts to climb up, as you can see here in this picture. It starts to climb up. And when it hits to about, let's say, it goes to about 200 and it's continuing to climb, you start to see that the garbage collection starts to get more aggressive and the frequency at which the garbage collection happens suddenly spikes. So it was not, in the normal mode, it was going between, let's say, 0 and, let's say, 4 GC runs. And then suddenly, when the memory is starting to climb and it goes beyond 300 megabytes, the frequency increases. Now, when the frequency increases, obviously the JVM's garbage collection is chewing more CPU cycles. And as a result, the CPU utilization also spikes at that point in time. Now, when the CPU utilization spikes, and because there's so much of work that the garbage collection is doing, you also start to see some pauses introduced because of the GC, right, the garbage collector. And that pause essentially results in a latency spike. So there's a causal relationship, right? Memory spiked, as a result, the GC frequency increased, as a result, the CPU utilization increased, and the GC pause essentially increased. And as a result of that, the latency also increased. And because of that, the performance of your application dropped. So each of the memories, GC frequency, CPU, and the in the pause and the latency, we need to study that as a sequence. Okay, when this happened, let's say 1 millisecond or 1 second later this happened, and 1 millisecond or second later something else happened, and so on. So we essentially need to take a window and we need to study in that window across the sequence of time steps. The time step would be milliseconds or seconds, what's really happening, to be able to make a prediction as to when will this latency spike and when will the application's performance drop. Let's say that is what your neural network is being trained for. We'll essentially need to understand that across the time sequence. Let me explain this using another simpler example. So let's say the data samples are like this, numeric in nature, 1, 1, 2, 3, 5, 8, 13, 21, and so on. And you're trying to make a neural network that's predicting what's going to come next. As a human, we have seen something like this many a times in our childhood. It's essentially a Fibonacci sequence. But there's some very unique pattern in this sequence. Essentially, in a Fibonacci sequence, any number, let's say you take 8, this number 8 actually depends on what precedes it. In the Fibonacci sequence, any number, let's say 8, is basically made up of adding the previous two numbers. So 8 is made up of adding 3 and 5, 5 is made up of adding 2 and 3, let's say 21 is made up of adding 8 and 13, and so on. So essentially, at any given point in time, if you want to make a prediction, you have to know what has happened before it, because the current number that you're predicting essentially depends on the order and the values that appear before it. So there are types of data where this is important. Obviously, text is one, we know that, because word ordering matters. When it comes to time series data, there's causal relationships across multiple metrics. So that it is very important to understand and study and train your neural network to acknowledge that. There is speech. The order in which you speak things is actually important because it conveys a different meaning if you change the ordering. So a feed-forward network is not really designed to solve for that, because a feed-forward network does not understand, nor recognize, nor has any way in which it can understand the ordering or sequencing of different things within the same training sample. And that's where you would need a neural network architecture that is different. And that neural network architecture essentially should treat any single input that's coming in as a sequence. So there has to be a technique by which we should take an input and break it down into sequence. That's one thing that we need. The second thing is that it also has to carry a certain amount of context or memory that basically tells the neural network that there is a relationship between what it has seen so far within the same training sample, that is. And what is happening now, like in the case of a sentence, when you take a sentence and you basically, like we said, right, she alone solved the problem versus she solved the problem alone. The word ordering, it's carrying some context, and as you get to the end of the sentence, once you know the context, you'll be able to decipher and say, okay, this is actually what it means. Okay, that is the type of neural network we need to build, an architecture that understands that. And that is where you essentially get a recurrent neural network. And a recurrent neural network is explicitly designed to solve for problems where your input data has to be processed as a sequence. So let's try to understand what a recurrent neural network architecture looks like. So again, the pseudocode I showed you here, I'm not going to repeat that again. This is for the feed-forward network. I'm showing that here because I want you to contrast that with what happens in a recurrent neural network. So in your feed-forward neural network, by the way, I can also pictorially depict it this way. You have your feed-forward neural network, FFN. You pass it an input, it makes a prediction, and you compare your prediction with the ground truth value that is there in your training data set. What happens in a recurrent neural network? Let's start with the pseudocode first. You would build a recurrent neural network just like I showed you how you build a feed-forward network. I will show you actually the specifics of how to do it shortly. But let's assume that there is a way in which you can build a RNN, and then exactly like the way you would feed data into an FNN during training across multiple training epochs, you would essentially start taking your training samples. Again, this doesn't change between an FFN and an RNN, but you start to see the change somewhere here. And the change essentially is that you basically take a training sample. So in the case of an FFN, you take the training sample here, it shows input, and you feed it into your feed forward network. The training sample in the prior example was the square footage of the house and the lot size it is on and so on. But in the case of an RNN, what you do is that you take the training sample, but before you pass it to your RNN, you split that into a sequence. So if it's a text, for example, it's a sentence, you split it into individual words. That's a sequence. How you split a numeric data, I'll show that later. But again, if there is a type of data, like say time series, there's a technique that you would use to split it. But for our understanding here, this suffice it to say that the input itself is split into different tokens. If you're taking a sentence, text sentence, then it's split into individual words. Now that actually becomes your input into your neural network. But before you pass it to the neural network for training, I also said that you need to essentially have some memory that captures the context between the different words in that sequence or different words in that sentence. You do that by first initializing some state. Typically, it's initialized to 0 because you are starting at the beginning of a sentence or beginning of an input sentence. And then you initialize that to 0. And now you essentially, for all the tokens in that sentence, which is essentially all the elements in that sequence that you have split your input into, you loop around and you pass the first sequence or the first word and the state that you initialized, and the training network that neural network that is being trained makes a prediction as to what should be the next word. Let's say you're doing sentence processing, what is the next word, and it also updates the state. Then you pass the next token and you pass the state that it is updated back into the neural network, and so on, and you sit in a loop and do this. And once you're done with that, then you go back and make the final prediction, and you compare your final prediction with the ground truth value, get the loss, back propagate that loss, and so on, which is again very similar to what you do in an FFN. So the big change here essentially is the training loop changes. A training as well as an inference loop changes between a feed forward network and a recurrent neural network. And the biggest change essentially is that you go from treating an input as one static black box in a feed forward network, you treat the input in an RNN as something that you can actually split into sequences, and then you pass the sequence one element at a time, the elements in the sequence one element at a time, and then you train a neural network that way. So the picture changes from just an input going into a feed forward network and a prediction coming out into something like this. You take the input, you split the input into sequences, pass it to your recurrent neural network. Along with that input, you also pass what we call as a state that allows us to capture the context that is flowing between all this, the sequence elements that we have split the sequence into. and then you loop around and process all the elements in the sequence, and then you make a prediction, and then you make a comparison. So that's how a recurrent neural network is actually designed at an extremely high level. Now let's kind of dig a little deeper and understand what's really happening underneath. Now, before we start studying the architecture of a recurrent neural network, I want us to go back and briefly look at the FFN model one more time, because I would like to go from showing pictures like this, where a network is drawn with the number of neurons in the front, the input neurons in the front, hidden neurons in the hidden layers, and so on, into using actual matrices, because that's how you'd actually see that in most of the online books or tutorials or the literature or papers, where you essentially use matrices to represent neural networks. So I wanted to introduce that nomenclature here so that we can essentially stick to that nomenclature instead of drawing out all these pictures. So, okay, let's look at this data again. In this case, again, it's a feed-forward neural network where there is no sequencing possible for each of those inputs, because here what I'm trying to do is I'm trying to predict the weight of a person if the input were the person's age and the person's height. So there is no sequence that you can establish between the age and height, or there is no relationship between age and height that that you could essentially graph out like in a sequence in a time series manner. So this is a good example where you can use an FFN. Anyway, so you have two inputs, so that can be represented instead of a picture using a matrix like this. X is basically x1 and x2. For the first training data, x1 is 23. The x2 is basically 5.8 for the same first training data. Now the hidden layer, instead of expressing it as this picture, I can essentially express this whole one single hidden layer as two matrices. The WX matrix, which is the weight matrix for this layer, which is W1 and W2 for the first neuron, W3 and W4 for the second neuron, W5 and W6 for the third neuron, and there are three neurons in this hidden layer, so there are three columns here. And then the bias is essentially B1 for the first neuron, B2 for the second neuron, B3 for the third neuron. So essentially, this is how you can take this picture and represent this using matrices. Now, in order to get to the next layer, you essentially have to first calculate the logits. Logits is nothing but you take the input signal and multiply it with the weights in that neuron. And now you're doing it across both these matrices. It's actually pretty trivial. What you do is that you calculate the logit as by multiplying this X matrix with the weight matrix here, WX, and then you add the bias matrix. And once you have that, you can pass it through an activation function before we take the signal and forward it to the next layer. Essentially, you're activating the signal strength from each of these neurons at this layer and sending it to the next layer. Here I'm using hyperbolic tangent or tan h as an activation function. You take the logit, pass it through the activation function, you get this value h. Now this h is the activated signal that's going from this layer to the next layer. Now what I can do is I can represent the next layer instead of a picture again as a matrix. The WY matrix here, I'm representing it has three weights, W7, W8, W9. I got this here. There's only one neuron, so that's it. There's only one column. And the bias matrix is BY with only a single cell, B4, because there's only one neuron in this layer. Now, in order to get the output, what I do is I essentially now multiply the H, the activated signal, with this weight matrix here, which is H times WY, then add the bias value. And once I have that, I need to send this to an output function. So let's say that I'm using softmax as my output function here. Let's say it's a classification problem, multi-class classification problems. I'm using softmax as my output function. And from that, I get my prediction, ypred. So as you can see, there's a very easy way in which you can take a graph-based representation of a neural network and represent that just using arrays. And the reason I'm actually using this here is because this allows us to, again, get away from using pictures, which is easy to understand but sometimes very hard to draw when your network becomes very big, to using actually matrices, because that's essentially how the computer also calculates anyways. Anyway, so let's now move forward. So you have your feed-forward networks represented using this matrix. I'm showing it here, X and the first matrix, second matrix, and so on. Now, one thing I would show you here is that I would actually rotate this matrix this way. Now, you might think, why are we doing this rotation? Essentially, the rotation is when you're taking this and then you're rotating it like this. It doesn't really change the math, it does not really change any computation whatsoever. The only thing it does is that it allows us to now treat the neural network in a slightly different way. For example, in this case here, I'm saying that the input goes from my left and the prediction comes out from my right. But if I just rotate it this way, then essentially what I'm saying is that my input goes in from the bottom, and then it comes out, the prediction comes out from the top. So you might ask this question, why are you doing this? What's the benefit of doing this? Because the math still remains the same. The only reason why we are doing this is because it actually makes it easier for us to draw a recurrent neural network and then represent it much more easier. Because remember, in a recurrent neural network there's a loop, and we'll study that shortly. But that is easy to draw if you essentially make the inputs go from the bottom and the predictions come out from the top, rather than going from the left and then the predictions coming out from the right. That's the only difference. That's the only reason why this rotation happens. The math does not change whatsoever. Okay. With this background out of the way, let's get back to our recurrent neural network. Again, I rotate it again just for the sake of making it easy for us to draw it. So even in the RNN, I would essentially rotate it. Okay. Now, let's try to understand a recurrent neural network a little bit better. Let's understand the sequence and the loop in the recurrent neural network. So this one, as you can see in the recurrent neural network, I take an input and I break it into sequence. If it's a sentence, I break it into individual words. And most of the literature actually shows the recurrent neural network drawn like this. Input goes from the bottom, and so does something called as a state, which essentially binds the context between the individual words in a sentence or individual elements in a sequence. And then you pass it to a neural network, it makes a prediction, you pick up the next element, and so on. So there's a loop here. So this loop, if I were to unfold, essentially it looks like this. Input goes in here along with the state, and then you would essentially have a recurrent neural network unit that processes that input along with that state, and then it makes a prediction. Now that state itself is updated, and that's the new state with the next element in the sequence or the next word of that sentence is passed along to the exact same recurrent neural network. It makes its next prediction, it also updates the state, and then you pass the next word in the sentence or the next element in your sequence along with the updated states to your exact same recurrent neural network to make its next prediction, and so on till you have exhausted every word in the sentence or all the elements in your sequence, and then you get the final prediction. So let's understand this using an example. So let's say I'm building a neural network that will make the prediction for the next word in a sentence. The cat sat on A. As a human, you know its mat is the ground truth value. That's what most likely it should predict. Okay. But you have to first take this input training sample and split it into sequence. So easy way to split that into a sequence is you tokenize it. And we studied different techniques of tokenizations in episode 1 of season 2, where I showed you white space based tokenization to byte pair encoding based tokenization and so on. For our example, let's say you are just tokenizing it at every word boundary. So the cat sat on A becomes the first element in your sequence. Cat becomes the second element in your sequence. Sat is the third, on is the fourth, and A is the fifth and the last element of a sequence. So it becomes a single sentence. One single training sample becomes 1, 2, 3, 4, 5. 5 elements of a sequence. By the way, if you get another training sentence, that becomes a completely new input and a completely new sequence. Essentially, an RNN takes one input and breaks that input into a sequence. Then it goes on to the next sentence, again breaks it into its own individual sequence and processes those words in that sequence. Okay. Anyway, so let's now take this example and map it to this diagram that we're seeing here. So what we do here is you build a recurrent neural network, and I'll show you shortly how you build that. So in that RNN, the ground truth value for this sentence in your training data set, it says the cat sat on it, the ground truth value is mat. Now you want to make this recurrent neural network make that prediction. But make that prediction by processing each of these tokens one at a time. So you pass the first token, which is the. Why first token? Because it's the first element in the sequence that you have split the sentence into. Along with that, you pass, as I said, a state. Because What you're doing here is a recurrent neural network has to not just treat the input as a sequence of individual elements, but it also needs to establish the context that flows between those elements to make meaning out of the ordering in which those elements appear in that sequence. So you essentially pass some state. So how do you select that state? I mean, the input is pretty straightforward because you are picking the input from tokenizing a sentence and picking the first word. But what about the state? The state is essentially another matrix that you essentially initialize to zero. We'll study that a little bit later, but just go with that. It's a new sentence, so essentially start with zero. So you pass this along with the first word. The neural network then does whatever it does and it makes a prediction. It should predict some word that comes after the. Along with that, it also updates the state that we have passed as another input. The input is the, of course, but also H0, which is the state. And it also updates that state and it passes that. So typically a neural network takes input and then makes a prediction, which you're seeing here, which is fine. But a recurrent neural network takes this input as well as the state value. It makes a prediction just like any feed-forward network does, but it also emits along with the prediction the updated state. Now you have to essentially now process the next token in the or next element in your sequence. So for that, you pass the next element into the exact same recurrent neural network. The recurrent neural network doesn't change. Like you see here, the first word goes in the, you pass it to the RNN. The second one goes in cat, that is processed by the same RNN. So you pass it to the same RNN. And what should happen now? The same thing. It takes the previously updated state, the new token cat, and it makes a prediction. And then it also updates the state. From H1, it becomes H2. Then you get to the next token, which is sat. And then it processes that, and then it makes a prediction again, and it updates the state and passes it forward. Then it picks up the next word in our sequence on, it makes a prediction, it updates the state, and then you pick up the last element in the sequence, which is A, and then this makes a prediction. So let's say its prediction is rug. It's a wrong prediction, which is fine because you're essentially initializing the training with randomly initializing all the weights. So it's expected to make an incorrect prediction, but it's fine because using the back propagation algorithm, by comparing its prediction with the ground truth value, you'll be able to adjust the weight so that after sufficient training, the RNN can make good predictions. So this example essentially gives you a very good illustration of what's really happening here. So let's understand the intuition behind what we have seen so far. I mean, we have seen the flow, but let's understand the intuition. So this is actually something like reading a book. When we are reading a book, just imagine that we are essentially seeing one word at a time, and we are sequentially processing it from left to right if it's English language. And as you're seeing these words, we also start to keep a summary subconsciously in your mind as to what we have seen so far. Now, if you think about it this way, if you start forgetting what we have seen so far, then each sentence and each word is independent of what's happened so far. So, if you do it that way, you really don't know what's being conveyed in that book or what is the story being told. The only way you know the story is because not only are you processing the words or the chapters as a collection of sentences and a sentence is a collection of words and you're processing it one word at a time, but you're also trying to understand what has happened in the past and you're trying to build meaning of what's really being said, and that's the only way you're essentially be able to figure out the story being told in that book. So we accumulate that state as we are reading through, and that is what the intuition here is, that we are trying to build something in an artificial world, which is the neural network world, to mimic what the brain does, which is essentially take something as input because it deems that this particular input could be broken into individual sequences. You break that and then you break it into individual words within that sequence and then process it while maintaining state. Of course, when it comes to reading a book, we try to keep not just the short term context which is there within the sentence, but you actually keep the long term context which is there across multiple chapters, multiple sentences, and so on. But that is actually done through another type of an RNN called LSTM, which we'll study in the next episode. But for now, think about the context being maintained by an RNN only in a single sentence at a time. Okay. It could also be more than one sentence. It could be a paragraph. Then you treat the entire paragraph as one input. Essentially, an RNN maintains a state across the entire input that you pass. The input itself is tokenized or created into individual sequence elements, and essentially it maintains the context flow within that particular paragraph, if you will. Okay, so that is the intuition. Now, let's look inside a RNN cell or an RNN neural network. Because if we think about it, going back to our familiar feed-forward network, input goes in, it gets multiplied by a weight, the value, the logit value, then is passed through an activation function. I show you tan h as an activation function here. The activated signal then is going through, multiple one or more layers, and it then essentially goes through the output layers, weight matrix, and then you essentially use output function and so on. In this network, if you look at it, again, there's a feed-forward network. There is no concept of passing anything else other than an input. But we said that in a feed-forward network, in addition to the input, which is the x values, you'll also have to pass the state. And the state is what is the one that is capturing the context across the different elements in that sequence. So how do you pass that? Okay. So now let's look at how a recurrent neural networks allows you to add additional context to what you already see in an FFN. So for that, I'll copy the architecture of an FFN over here from FFN to RNN. And as you can see, there is absolutely no difference whatsoever between the FFN and the RNN architecture at this stage. Same thing, input goes in here, multiplied with the weights, you get the value of the logit, pass it through the activation function and so on. But how do you pass the state? The state is passed actually in a very simple manner. What you do is that you add another weight matrix. Okay. This weight matrix is one single weight matrix for your entire RNN network. It's not like each layer of your neural network has a different weight matrix. For your entire RNN, you add what is called as a context weight matrix, and I'll denote that using WH. Don't be confused by these numbers. These numbers have no continuity or meaning. It's basically a certain set of weights. I'm just showing as an example that it has 100 weights in the input layer, and it has 100 weights in the the context matrix and so on. It's not like this is a continuation here. It's an independent matrix called WH in the literature. Now then what you do is that you essentially pass a hidden value here, or rather you pass a context value here. And that context value, because at the beginning of a sentence here there is no context, you're essentially starting at the beginning, so you essentially pass zeros. So this is what you do to add a variable called state, which was lacking in a feed-forward network. But what we also need to understand here is this value has to now influence what's happening inside this neural network. And the way you do that is, if you look at the feed-forward network, you essentially had the input being multiplied by the weight matrix and added to the bias here. What you do with a recurrent neural network is that in addition to that, so this remains as this, but you also add the multiplicative value of the h, the state that you're passing, which is initialized to 0 at the beginning of a sentence, with this weight matrix, and you add that together, and then you pass it through the activation function, and the rest of it remains the same. That's the only change that you're making, okay, to a FFN to make it look like an RNN. Okay, now one key observation to be made here. When depicted like this, with x going in from the bottom, and x being the input and h coming in from the left here, you're missing out one key part, and that key part is in a recurrent neural network, the elements within the same input is processed as a sequence. So essentially, one element of the sequence at a time needs to be processed. So there's a loop, and that loop is best expressed in terms of time steps. Essentially, if you take x here, and let's say the sentence is the cat sat on A, so it essentially the is one word, cat is a second word, on is another word, and so on till A is the last word, and so on. You essentially have this. And then you have the previous state also that's going into your RNN. So maybe the best way to express this is in terms of time steps. You basically say at time t1, you pass the input that you see is the first input of your sequence. So that's t1. But you also pass the previous state. There is no previous state when you're beginning, so it is essentially h0. And when you pass that, you essentially get h1, which is the updated state. So essentially like this, let's say the current token, let's say it's x2 here, which in the case, the previous example is the cat sat on a mat. So the is the first one, cat is the second one. So essentially the current token, let's say, is cat. To that, you're passing the previous state, which, so let's say cat, right? You're passing what came out from the back, from behind, before it. So you're passing the previous state. So in the state from the previous time step, which is this time step, is being used along with the input from the current time step, which is this, and passed to the neural network so that it can calculate the updated state at that is going to be fed to the next time step, which is xt. So ht. So ht is calculated by taking xt, which is the current input, and the previous state. So new state is calculated by processing the current input and the previous state. So this way you establish a relationship between what happens, let's say, in this time step with what has already happened in the prior time step. So similarly, what has happened in this time step is determined by this value h, which is calculated in the prior time step, is updated in the prior time step. So what you have done here is that you have established a way in which you can maintain the time sequence in which you're processing the individual elements in your sequence. Okay. So far, we have established two things. Number one is how do you introduce the concept of a state to a neural network that was lacking in feed-forward network? And again, as a summary, it's very simple. You essentially just add one more matrix, which is made up of trainable weight values, and then you add externally to that a state that you pass to your neural network. Okay. So that's the first thing that we have understood so far. The second thing that we have understood so far is that the way you need to look at a neural network, a recurrent neural network, is that you're processing things in a time sequence manner. And each one is called a time step here. X1 is the first time step, X2 is the second time step, X3 is the third, and so on. And at any given point in time, the current input at this current timestamp with the state value from the prior timestamp was together used, right? Together used to compute the prediction of the current timestamp. Okay. But then what about this loop? We see this right now. You essentially take the input and then you process that in a loop. How do you introduce a loop here? That's also pretty simple. So let's say the first timestamp you get the input here, which is in the case of the cat sat on and you're initializing the previous state. There's no previous state. So essentially start with h0, which is essentially all zeros. And then you calculate, as I said, a prediction, which is y pred1 here. But you also emit the updated state here, the previous state and the current, rather the input from the current time step, the input from the state from the previous time step, both together update the current state, right? H1. Now you pass that to the exact same neural network. It's not like a new neural network. Essentially, in a loop, you pass that back into the same neural network. Pick up the next element in the sequence, which is cat here, the cat here, and the updated H1, you pass it here, you calculate the updated state for at this time step, pass it forward, and so on till you hit the last one and you make a prediction. So it's pretty straightforward. Now let's dig a little deeper. I want to explain the concept of how a training happens in a recurrent neural network using this pseudocode, because I think it's very important to understand the internal details as well as also understand how the weights are adjusted. So for that, I wrote this very small program that illustrates how training happens in an RNN. So what I've done is, and again, I've not used any library. I've just used NumPy. I've not used a neural network library, just NumPy to explain all of this, because I think that's the best way to actually understand it, by hand rolling your own implementation to see what's really happening. So what we do is we are trying to make a prediction of what would be the next word given a sentence. Okay. And my training data set essentially has things like the cat sat on a That's the input I want to give, and I want that neural network to train itself so that it can make a prediction called MAT. So it's basically an array in which you have each row is made up of an array with two elements. The first element has the sentence, and the second element has the word that it's supposed to predict. If, for example, the second sentence in the training data set is the dog played with a, we are supposed to train the neural network to predict ball. Anyway, so what I do is that, let's say I have some word embeddings that I'm using. The number of dimensions for that embeddings is 16. I've explained what word embeddings is in episode 2 of season 2. I'm not going to repeat that here. And let's say you have about 10,000 words in your vocabulary. And you're building your H matrix as a 32 dimensional hidden state. There is no set and fast rule as to what should be the right value for your dimensions. You pick one and see if it's not learning the context well, then you essentially can increase it. But essentially, what happens is the way you initialize this weight matrix, and essentially also this H0 value, is by selecting some dimension for that. Let's say here I'm selecting 32, and then you create a matrix of n by n, so 32 by 32 size matrix. Okay. Anyway, so for our neural network, I will need to have weight matrix Wx, which is here. And then I randomly initialize that weight matrix. I create a bias matrix, which is initialized to 0. We have studied this in season 1 quite exhaustively. How do you initialize weights and how do you initialize bias? Instead of using random for weights, you could use the Xavier initialization or he initialization or what have you. You also initialize WY. You can see here, I'm randomly initializing in this example. I initialize bias to 0. And the WH I initialize to random again. Okay. Now, across multiple training runs, I'm doing it 1,000 times. I pick up the first sentence of my training data set, the cat sat on it. I'm supposed to first create a sequence. In text, it's very easy to create a sequence because all I need to do is tokenize it. So I'm going to tokenize it. So the cat sat on it becomes essentially a token list of tokens of 5 words. The cat sat on a. That becomes some input tokens, and my prediction y true value essentially is mat, and that's what I need to train my neural network to predict. Okay, now I need to initialize my state, which is h0 here, which is I'm initializing to all zeros. Why all zeros? Because I'm beginning the sentence and there's no state to actually carry forward. So I initialize the state to all zeros. Then I also create two arrays called h states so I can capture the updated states that are happening across all the elements of my, of my run, of my sequence. And then I also capture all the outputs that are coming out from the individual, you know, sequence. From the and I also capture all the outputs that are coming out, like the y1, y2, and so on, that are being predicted by the neural network based on seeing each individual token of that sequence. So, okay, now I have all the sequences across each time step of that sequence. I'll pick up the first word, extract the embeddings from, pre-calculated embeddings. Let's say I'm using glove or word to egg. I'll take the word and get the embeddings because neural networks do not understand text. We need to get numbers, and embeddings is the way to get numbers from text. I've actually explained how to do that in episode 2 of season 2. You can review that if you forgot. But anyway, so you take the word and get its word embedding. So that becomes your x. Okay. Now you need to multiply x with wx. We saw that. X with wx times 1. X with wx. Add to that the bias value. Add to that the bias value. Then you multiply h, which is initialized as all zeros, with this weight matrix, which is all random, initialized to all random. Then you pass that through an activation function, which you can see here, tan h. And then you take that h value, that's the updated h value. You save that, like I'm saving it in the h values here, because you need to pass that to the next state, correct? Or next token in that same sequence. And then you make a prediction. And you make the prediction by doing what? You take the h, you multiply it by wy, h multiplied by wy, and then you add to that the bias value by, and then run it through a softmax function. Then you get your prediction. And you save your prediction also, y pred 1. That's becomes your y pred 1. And then you go loop around and pick up the next token in the sequence, which is cat here. then you get cat, you get the word embeddings for cat. And now you take the word embeddings for cat, multiply it with the weight matrix here, Wx, add the bias matrix, and then you take the value of h. Now, h, notice, essentially was updated in the prior run, correct? And then you take that updated state and then you multiply it with wh, run it through the activation function. You save the value of h here that you updated so that you can propagate it to the next state or next element in the sequence. You make the prediction, you also save your prediction here. So, and this keeps going on till you have exhausted all your tokens. Once you have exhausted all your tokens, which is you've gone past A, at this point, you have made a prediction. The last element that comes out of this, or last prediction that comes out of this, is the word that you're trying to predict as the next word in the input sequence, the cat sat on A. Now, this prediction could be wrong because, and most likely it is wrong because initially you're starting off with random weights. Now you have to adjust those weights so that your prediction gets right, correct? So for that, again, this is a multi-class classification. So I take the ground truth value, which is mat here, and then I take the final predicted value. I'm storing all my intermediate predictions in this outputs array. So I take my final value. I calculate the loss using cross entropy loss. Now I need to adjust the weights back. Now this is one change here. In a feed forward network, you would use a back propagation algorithm. Essentially, in a back propagation algorithm, what do? So there's a neural network. You start with the back of the neural network, which essentially is the output layer. You adjust the weights there, then you go back to the previous layer, you adjust the weights there, then you go back to the previous layer, adjust the weights there, and so on. That's exactly what you do in an RNN, but with one twist. And the twist here is, in addition to back propagating, just like in an FFN, you also have to acknowledge that in order to get to this state, getting to the final prediction, you actually had gone through a loop of doing this. So you have to actually go through this back propagation once. You also have to go back in time from the X time sequence here to the previous time sequence, to the previous time sequence, and to the previous time sequence, and so on. So what I'm showing you here is that I know in reverse I'm going through all the tokens. So I start here with A, adjust the weights for that, adjust the same, essentially adjust the weights in the neural network for once, then also go back to on, adjust the weights of the same neural network again, go back to SAT, adjust the weights of the same neural network again for SAT, and so on till I'm done with all the sequences or elements in the sequence, correct? That's one big difference. Essentially, in a feed-forward network, you only do back propagation. In a recurrent neural network, you do the back propagation, but you also back propagate in time. Okay. Now, one question that obviously jumps out here is that I've only calculated loss once, and I'm using the same loss to calculate the weight differences and the gradients for all these weights once, and even in the prior timestamp and the prior timestamp and so on. Why don't I use these weights, these predicted values too, the intermediate predictions too? You can. Typically, what happens is that if your problem you're trying to solve is predicting the next word that follows the input, then you're only interested in the prediction that is happening at the end. Correct? Here, I'm only interested in the prediction that's happening here, which is mat. So then you would only use the final prediction because you're taking the difference between the final prediction and the ground truth value. But there are certain tasks like language translation. So you're going from, let's say, English to Hindi or English to French or something like that, or Spanish to French, where each word you have to make sure that it's predicting the right word in the different language. There you would actually do the loss across not just the final one, because now you're not just interested in the final word, you're essentially interested in word for word, is the translation correct or not. And I'll actually talk about that kind of a model 2 episodes down in a thing called sequence to sequence modeling. But for now, just suffice it to understand that in a recurrent neural network where you're only interested in the final prediction, you just take the loss value once. You calculate the loss value from the final prediction and compare it with the ground truth value. In sequence to sequence models where you're trying to do language translation tasks, then you'll also do the loss across the intermediate predictions. Okay. So this is how prediction happens. And this is how weights are adjusted. Now you're done with the first sentence. You go back, pick up the next sentence in the training sample set, which is the dog played with it, and you're expected to present predict ball. Now you see again the state is reset back to zero for the second sentence. Why are we resetting the state back to zero? Why not continue it? Because you updated the state here. You have to reset it back to zero because you're seeing a new sentence. You're trying to build context between or across the words within that sentence. You're not trying to build a context across all the sentences in your training data set because each individual training sample in your training data set is independent of the other. It is just that within a single sample, you want to understand the ordering of the words. Now, if you say, hey, no, I won't actually take multiple sentences and build context, then that becomes that multiple sentences, your entire paragraph becomes one training sample. And you essentially initialize the state once to zero in the beginning, and then you keep on updating the state across all the sentences in that paragraph because that is again one single input. So that is the reason why you reset the state back to zero whenever you see the next input in your training data set. All right, and the rest of it remains the same. So this is how the logic of training happens. This is how the weights are adjusted in a recurrent neural network. Now, one other question that we want to ask here is we started this episode by saying that the benefit of an RNN is that it allows us to study the context between or the context that is flowing between all the words in a sentence. Just by adding this weight, how are we essentially accomplishing that? It's an obvious question that we would all obviously get. The way to understand that is the following. Actually, there is no magic here. And what you want to do is that, assuming that there is some context that flows between words, let's make that assumption. And I think it's a safe assumption that there is some context that flows between words, and that is how we are establishing the meaning of a sentence, we meaning humans. And the fact that humans are the ones that have invented language, and they are the ones that have formulated these rules that are subconsciously almost burned into our brain cells, that this is the language, this is the ordering in which words need to appear to make meaning. The neural network basically says, okay, the human is giving me some sentences, and those sentences, obviously, the human has deemed as they mean something, which means that there is already some context that is established, between those words by the human. I just need to build a model that ensures that that context is retained as I'm learning it. Okay, it's not doing some discovery that a human does not already done. It's basically taking input that a human is deemed as correct, and then it's trying to understand the rules where that establishes those connections between those words. The human is not expressing those rules, right? The human is not giving a grammar book along with the input training data. Human is saying these are the correct training sentences which we as humans feel that they are correct. You figure out the rules that establishes the context. And what is the right way for a neural network to establish that rules is by using weights which are initialized to all random, and then to making predictions, and checking whether the neural network's prediction is consistent with the human's expected prediction, and adjusting those weights, it can figure it out. That's exactly what's happening here. You throw in a weight matrix, which is lacking in a feed-forward network. We'll call it a context matrix. We initialize it to zero, and we start studying the training data set. And then we'll adjust the weights. And at some point, our predictions are going to be correct. As our meaning the neural network's predictions are going to be correct. At which point, we know that the neural network has all figured out what is that context that is flowing between words of the same sentence. That is exactly what's happening here. Okay. So this is our training. Now let's look at what happens during inference. During inference, let's say the sentence I'm getting is the cat and dog. By the way, when you're getting to inference, it also means that you already trained your RNN and the weights are all adjusted well now and it is able to do the right predictions, correct? So I'm going to give it a sentence called the cat and dog, and you want it to make a prediction as to what the next word is going to be. So it's a new sentence. I essentially again initialize the hidden state to or the context state to zeros. Not the weight matrix. The weight matrix is all adjusted as part of the training, not this one. Essentially, the inputs to the neural network are what? One is the input word, the word itself, and the other one is the context state, correct? It's a new sentence or new sequence. So essentially, I'll initialize it all to zero. I tokenize my input because recurrent neural networks need to see tokens or rather sequences. What best way to tokenize or sequence a text thing than tokenizations? I tokenize it into individual words. I pick up the first word, get the meaning or get the embedding for the first word, then do that embedding times the weight matrix plus the bias matrix plus the multiplication of the context state and its matrix h times wh, and then I update the state here, pick up the next word in my sequence, which is cat. Cat goes in here. Embedding of cat is multiplied with the weight matrix plus the bias matrix. By this time, WH, WX, and BX are all trained in the prior training run. Remember, we are doing inferencing here. Pass it through the activation function and so on. Keep on going, because I'm not interested in these outputs at this stage. I'm only interested in the last word that is going to be predicted. So I ignore the rest of it here. I go through all the words in my sequence. So the cat and dog. Now that I've come to the last one, the dog, what I need to do now is actually to process even the final output so that I can make a prediction. So for that, I will see how many words do you want me to predict. Let's say I want to predict the next two words, the cat and dog. Maybe I want to predict played with. So I'll go through those many number of words I want to predict. I'll take the value that is coming out from here, which is the H value, which is the H value here, multiplied with a pre-trained, WI matrix, add it to the bias, run it through a softmax. A softmax gives you a probability distribution across all the possible words in my vocabulary. Then I look and it'll give me an index. This is the index with the word that I think is the highest probability, which is the correct next word for the sequence. Then I'll print that out. We'll come to the end of sentence shortly, but I'm going to print that out. Then because I wanted to predict two words, so I'll basically take the new updated H value and I'll loop through again and I'll calculate, the values just like in the past that you've seen in this loop here. Now, but when does it stop? It can stop either when you tell it how many other tokens it needs to predict, or it can also stop when it sees the end of sentence sequence. It's a special sequence, or a token rather, end of sentence token, which is a special token. How does it know end of sentence token? Because typically, when you're training a recurrent neural network, and later on in season 3, when I show you transformers, you also need to tell the recurrent neural network that as a human, we deem that this sentence is completed because it is seeing an end of sequence token. And it also learns when a sentence begins, when a sentence ends, and as a result, it will also be able to put a period when it's emitting out the next word. Okay, so essentially stop your inferencing either when you see an end of sentence sequence or when you see, even you already generated the maximum number of tokens that the user wants to generate. So this is how inferencing works. One key observation here is that in order to make the prediction, you have to go through all the words. If you want to make 10 predictions, you still have to go through all the words, make them, let's say in this case, you have 1, 2, 3, 4. The cat sat on it. So you have 4 words that are given as an input, and you would like to make a prediction for the next 3 words. So essentially, 4 input plus 3, 7 total tokens you want. So you go through the first token in the input, second token in the input, third token in the input, fourth token in the input. Then you make the prediction for the fifth token. You take the fifth token, make the prediction for the sixth token, take the sixth token, make the prediction for the seventh token, and so on. So you just cannot say, oh, give me the seventh token that you would predict. No, you cannot. In a recurrent neural network, you have to make all the predictions before the seventh to make the seventh token prediction. Okay. So this is what also called as autoregressive in the sense that you need to predict what has happened in the past till you get to the slot that you would like to predict at. Okay. Okay, now that we have understood the new what a recurrent neural network is, we have understood the limitations of a feed-forward network that the recurrent neural network RNN addresses. We have understood the high-level overview of what it does, how it does it, why it does it that way. We also understood the intuition behind why you need it, and we also understood the code that you would write to implement it if you were to do it from scratch. Now, what we want to do is that we actually want to see an RNN being used in real world use cases. For that, what I will do is that I'll show you how to use an RNN to do two things. Number one is how do you make time series forecasting, which is numeric in nature, and I'll also show you how to do text generation, which is like what the Google or the Gmail Smart Compose did way back in 2018, which is built on top of in a form of RNN. Okay, so before we see the code, a few things to understand here. So when you're training a recurrent neural network, or even when you are doing inferencing, one key thing that you need to understand in an RNN is this step here. Let's say you're passing a time series data which is numeric. An RNN needs to understand the context that is flowing across that input, which means that the input itself needs to be broken into individual sequences. With text, it's very easy. It's a sentence, you tokenize it, and that tokenization essentially can be used to create sequences where you essentially treat all the words of a sentence, single sentence as a sequence, and so on. But when it comes to time series data, so let's say that you're trying to capture the system metrics like the CPU memory utilization and the storage IOPS and so on every let's say every minute for the every day, every minute, every day. Then you have to create a sequence. So you essentially, because you want to make the RNN actually understand what's happening across multiple minutes of the time series data. So the first thing we need to understand before you actually see the code is how do you take input and create sequences? And the way you create sequences between numbers and text actually is different. So we'll study both of them. So let's start with numbers first, time series forecasting using RNN. Okay, so let me go to actually this one here. And let me show you how you first create the sequences. So let's say that your time series data looks like this. The first training sample is 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, and so on. We have more and more such training samples. So the first thing you want is you want to understand what is happening, let's say every hour. Okay, I'm collecting my samples every minute. So there are essentially 60 minutes in an hour. So I want to say that, okay, my sample is, my sequence is going to be every 60 samples forms one sequence, if the next 60 forms a second sequence, and so on. So that thing, the 60 that I'm using here is actually a window, okay, the sequence window. So let's say that your time series data is like this and your sequence is 4, which essentially means that let's say you're collecting data every second and you would like to understand every 4 seconds what within that 4 seconds what's happening, then you would pick the window size of 4. And when you do that, the way you create sequences is you take the window size is 4. So you take the first 4 things that appear in the input, like say 10, 20, 30, 40. That becomes your input. And then you're predicting what happens next, which is 50. Then you predict the next one. So 20, 30, 40, 50, which is 4, 20, 30, 40, 50. And you predict the next, which is 60. Then you move one slot next, which is 30. So 30, 40, 50, 60. So 30, 40, 50, 60. What is coming next? 70. So you predict 70. You're training the neural network to predict 70 and so on. So let's say you come here like 70, 80, 90, 100. So sorry, no, you're at here 60, 60, 70, 80, 90. You're predicting 100. Okay. Now, when then you move one slot and then you say, okay, 70, 80, 90, 100, but there's no other prediction because the input was given like this. So you stop there. Okay. Then you pick the next training sample 1, 2, 3, 4. So essentially, you say 1, 2, 3, 4. I'm supposed to predict 5 because that's the thing that appears here. Then I move one slot 2. So 2, 3, 4, 5. 2, 3, 4, 5. And I need to predict 6 and you stop. So this is how essentially you would create sequences out of numeric data. Okay. Now with this, let's go and actually look at a practical example. So let's start with an example here. So I created a Google Colab notebook, and what I want to demonstrate here is using two examples. In the first example, I will show you, actually in both examples, I want to run the same data using both the feed-forward network as well as a recurrent neural network. What I want to demonstrate, in addition to showing you how to use an RNN in real life cases, is to also demonstrate that not all types of numeric data can benefit from an RNN. Okay, And there is certain types of data that can benefit from an RNN and an FFN will actually fail miserably. That's what I want to demonstrate. So you take away not just how to use RNNs for solving real life use cases, but also understand that in some cases an FFN is sufficient and RNN is not really required, although it can also solve the same problem that an FFN does. Okay. So here I have my Google Colab notebook. I'm importing certain libraries, which is fine. There's some common code where I show you how to prepare sequences and all that. And I also show you how to build the recurrent neural network and feed forward neural network. We'll come back to that shortly. Let's actually go here and try to understand this. So this is an example where I'm showing you where an FFN and RNN can actually predict well. Okay. And the kind of data here is as follows. I'm essentially creating a sinusoidal pattern. Essentially, at any given time step, the value of is predicted as sine of the current value. This is the Python code that shows you how to build the data set. Now, what I do is that I get the data set, I create 100 samples of the data set. Now I need to create sequences because again, I need to pass to an RNN sequence data, correct? So I'm essentially, let's say this is a sine wave that looks like this, something like that. I figure out my sliding window. So my window size is 10. I would create sequences. And again, I showed you that the way you create sequences is that if you get the input data as 10, 20, 30, 40, 50, 60, and in this case, let's say sequence is 3, you would essentially split it as 10, 20, 30 is your input, prediction is 40, 20, 30, 40 is your input, 50 is prediction, 30, 40, 50 is input, and 60 is prediction, and so on. That's exactly what I'm doing here. I'm breaking up my 100 data points into a window of 10 data points that I'm going to be inspecting as a sequence. Now I'll build a recurrent neural network and I'll also build a feed forward neural network. So let's understand how we do that. Let's actually study a feed forward neural network first before we get into RNN. So feed forward neural network is built as the following. You create a sequential using the Kira sequential library routine. I'm passing it as 10 inputs, let's say 10, 20, 30, 40, like an example that I showed you. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And then I'm going to create one hidden layer, which has 30 neurons in it. I'll use an activation function of ReLU. And one output layer because I'm just trying to predict one number that appears after the input. And then I compile it. I'm using Adam as my optimizer. I'm using mean squared error as my loss function. MSE is good because I'm predicting numbers here, so that's fine. Then I summarize it. This is how a feed forward network is built. Because remember, I'm trying to pass the same data through a feed forward network as well as an RNN, and I want to understand how each one predicts. So how do you build an RNN? The way you build an RNN is actually pretty simple. So you say that I'm passing my input shape as this again. I'm passing 10. My input is divided into sequences of 10 elements. And then I create a simple RNN. The first parameter here, 50, essentially says that the weight matrix that I'm building inside my neural network, that the WH matrix is going to be a 50 times 50, 50 cross 50 matrix. That's what it means. And then I have one dense layer that makes a prediction with one one neuron in it because I'm just predicting one number that comes after the first 10 inputs that I'm giving. I'll use the same Adam optimizer and mean squared error as my loss function. So let's run that and see. Okay, so we have run this here. I'm building the RNN, I'm building the FFN, then I'm going to run RNN.fit to train the RNN, and then FFN.fit to train the feed forward network. Then I make the predictions. Before we see the code for the predictions, let's actually go and see, plot the data. Okay, let's see what this code has done. So by the way, when I build the RNN, how many parameters does it have? It has 2651 parameters. Okay. If I build the FFN, it has how many parameters? 361. So as you can see, an RNN actually is a much bigger neural network for the same input than your FFN, even when you choose the weight matrix just to be a 50 cross 50 size weight matrix. Now, in this data, as you can see, or in this input, as you can see, both and by the way, the green dots here, by the way, the blue lines is basically the historical data that you pass as input. And the green dots is basically the predictions that is made by the feed-forward network, and the red dots are the orange dots are the predictions made by the recurrent neural network. And as you can see, when I'm making how many predictions am I making? We'll come back to this code shortly, but I'm making 40 predictions. What you can see here is that both the feed-forward network and the recurrent neural network have done pretty much the same. Their prediction accuracy is pretty much the same. So why are we doing this then? I mean, how is it that we said that in a recurrent neural network actually is better to understand time series, but here it seems that both of them are predicting the same with the same accuracy. So what's going on here? So what's going on here is that the type of data that you have here, a value here, for example, does not depend on the value that comes before it. Why? Because essentially the data is structured this way, the sinusoidal data. So the value does not really depend. So sine of x, it does not depend on the value that comes before it. I mean, if you had something like this, not like the value of this one, y, is based on sine of x of I plus something, let's say y of the previous value, I minus 1, then you know that the current value depends on the previous value using some logic like this, correct? But that relationship is not there when you're just doing pure sine wave kind of a data. So that's the reason why your RNN, while it can predict just like your feed-forward network, is an overkill to solve these kind of problems. You would not really choose an RNN when you can essentially make do with just an FFN. Look at this. An RNN has 2,651 trainable parameters, whereas a FFN has 361. So by the way, okay, now so you understand that, but let's understand what I did to make these predictions. So I want to make the next 40 predictions. And as I told you earlier, to make the next 40 predictions, you have to make the first predictions after the historical data, then the one after that, then the one after that, and 40 such predictions to get to the 40 predictions. So what you do is that you actually copy the last window worth of data. I think the window that we defined here earlier was the sequence length is 10. You copy the last 10 data points here. So you predict the one after that. Then you slide this forward to copy the next 10, make the next prediction, copy the next 10 to make the next prediction and all that. That's the kind of code you need to implement here. This will become more clear when I show you text, but the logic here is that you copy the last 10 data points from your historical training data set, and then you pass that to RNN.predict. Similarly, you pass that to FFN.predict, and you make the next prediction. When you make the next prediction, you use this thing called np.roll, which is nothing but because you want to make the prediction after that. First prediction is made. You want to make the second prediction. To make the second prediction, you essentially move over. So you essentially say, okay, 10, 20, 30, you predicted 40. Now you have to give 20, 30, 40, and you have to make the big prediction called 50. See, this np.roll just left shifts your data so that it will make room where you can insert, the just currently predicted value, and then you pass it back and it makes the next prediction called 50 and so on. So that's what you're doing here. This becomes more clear when I show you text, but so just go with this, or you can inspect the code yourself and you will understand it. It's pretty straightforward. Anyway, let's now move to the next demo. So what I do in this demo is I want to show you where a recurrent neural network makes the right prediction and the FFN fails. And like we discussed before, the kind of data where that happens is where there is a dependency or a context that determines the relationship between the data points within the same sequence. And Fibonacci sequence is great that way because the current value depends on the last two values. Yeah. So that way I know that, a Fibonacci sequence, if I were to pass that to predict the next Fibonacci sequence without giving it the formula, and if the neural network is able to do it, RNN, and you will see that RNN can and feed-forward network cannot, you know that when the data has that kind of a relationship, then it is important to use an RNN and not an FFN. Okay. So what I will do here is I will generate the data. Let me run this code. I'll generate the data, and I'm generating the first 20 Fibonacci numbers. Then I'm going to create a sequence of 5, which means that I will take the first 5 Fibonacci numbers to predict the sixth, Then I will take the next 5 starting at the second one to predict the seventh. Then I'll slide one over, pick the next 5 to predict the third, and so on. That's what I'm doing here. What I also do is that I scale the data using a min-max scaler so that the values are between the -1 and 1 range. It's like the normalization, the input normalization that I taught in episode 2 of season 1. The reason why we are doing that here is because you know that the Fibonacci number sequence essentially gets very, very large very quickly because you're adding up two prior numbers. And you really don't want the value, the size of the value, or the magnitude of the value to influence the outcomes. Because when a large value is multiplied with the weight matrix, it produces a large value. But that doesn't mean that it carries a bigger influence in the sequence. So the min-max scaler essentially allows us to scale the data, all the data points between a -1 and 1 range. How it does this, you can look it up outside, but it's basically just like the input normalization technique that I taught you in season 2 sorry, episode 2 of season 1. Anyway, so we generate the data. We generate 20 Fibonacci sequences. Okay, I normalize the data. And then I break it into sequences, which means that break sequences of 5, length of 5, which means that the first 5 Fibonacci sequence numbers are fed in to predict the sixth. Then you slide one number over, then the second, third, fourth, fifth, sixth are fed to predict the seventh. Then you slide one over, then you predict fourth, fifth, sixth, seventh, then you predict eight, and so on. And then you build the RNN and FFN just like I showed you earlier. Let's just go back here and revisit the code once. The RNN is built as, simple RNN is the inbuilt routine. You create a weight matrix of 50 times 50, which is your context matrix. You pass in, in this case, the sequence length is 5, so you pass in 5 as my sequence length into a simple RNN, and you emit one value, and so on. The FFN is built by passing in the first 5 values, and then you pass it through a hidden layer which has 30 neurons in it with a ReLU activation function, and you make one final prediction. Okay, so let's go back here. We run that through the training data set, and then we go ahead and predict. But before we go and see this code, let's look at what has happened here. Okay, so in this case, as you can see, the correct value for the next 5 are supposed to be 6765. The RNN predicts as 6765. Look at the FFN. It predicted 1971, which is way off, which is completely incorrect. The Fibonacci numbers that comes after that, the correct value should be 10946. RNN predicts it correctly. FFN is completely off. The next one is supposed to be 17711. RNN predicts as 17712, which is very close. And the FFN is completely off. And so on. So as you can see, if the data basically has this pattern where the current sample depends on the samples that come before it, your feed forward network is terrible at identifying the pattern, whereas a recurrent neural network is very good at identifying that pattern. And the only reason why is because a recurrent neural network has this context vector that we have created, context state, and we study that context flow across all the elements in the sequence. And in this case, the sequence we are determined to be 5, which means that across the 5 Fibonacci sequence numbers, we are essentially studying the pattern. Then you pick up the next 5, study the pattern, and so on. So it's also learning that context that is moving across the sequence. And as a result, it's able to figure out that, hey, you know what? The next number that you want me to predict actually needs to leverage the fact that it depends on the prior two numbers. For example, in the Fibonacci sequence demo that we are seeing. So this is how you would use feed forward networks or recurrent neural networks to make predictions. Okay. Now let's look at the second type of problem we'd like to solve using recurrent neural networks, which is text generation. Okay. So before we get into the code, I want to give you some context as to how do you do sequencing when it comes to text. There are two different strategies. Let's try to look at that, and let's also look at what happens when those sequences are created, and then we'll get into the code. Okay. So let's say the input training data is the cat sat on a mat eating her food, and the second sentence is the dog chased the cat around. So you want to tokenize it. But then how do you create the sequence itself? So you can basically say, hey, the way I'd like to create a sequence is that I want to create a sequence length of 4, let us say. Then I pick up the first word, 4 words, like the cat sat on A, and then, sorry, cat sat on, and then the ground truth value I want to predict as A. Then I will slide the window over. Then I say the cat sat on A, and the next value I want to predict as Matt. And then I want to slide one word over, and then I want to take the next 4 words because my sequence length is 4. Sat on a mat, and I want to predict eating, and so on. So as you can see, even though my training data has only 2 samples, using the sliding window, I can essentially create about 7 training samples. And essentially that way I can predict. Essentially what you're saying is when I see the cat sat on A, predict A. When you see cat sat on A, predict mat. When you see sat on a mat, predict eating, and so on. Correct? That's one strategy. There's an alternate strategy, and the alternate strategy essentially used to use what is called as n-gram based strategy, where you say, take the first word, try to predict the next word. So take the, predict cat. Then they take the first 2 words, the and cat, and predict the next word, sat. Then they take the next 3 words, the cat sat, and predict on. Then add that on to these things and say the cat sat on and predict A. Then you say add A back to this list. The cat sat on A and then predict mat, and add mat back to this list. The cat sat on a mat and then predict eating, and so on. So this way, from just the 2 training samples, you could essentially create 13 different training samples that you can train your neural network on, which is great. But there's one drawback. The drawback here is each of these inputs have different lengths, and the neural network needs to have a fixed length that needs to go in because it has a certain fixed number of input neurons. So how do you make it fixed? We actually looked at that in season 2, episode 1, when I taught you tokenization. You essentially determine what would be the maximum length of any sentence in your training data, and you can observe all the sentences and figure out what is the maximum length, or you can pick some very large number, let's say 1,000 or something like that. Your sentence will have no more than 1,000 words. That's what it means. And then what you do is that, if your sentence is less than that, you pad it with the rest of the tokens. You just use the special pad token. Essentially, you do something like this. So one interesting thing that you see here, by the way, I'm using maximum sentence length as 1, 2, 3, 4, 5, 6, 7, 8. So which means that because the first training sample has only 1, I'll pair it with 7 special pad tokens. Now that way all my sentences have a fixed length. Okay. But one thing that you notice here is I'm not doing the followed by 7 pad tokens. I'm doing 7 pad tokens followed by the. Why do you think I'm doing that? The reason I'm doing that is because we are trying to build a recurrent neural network that predicts the word that comes after that. And this is where the ordering matters. If let's say the thing was the pad, and cat, it makes no sense. What does the pad, cat mean? Nothing. However, pad, the cat makes some sense because the cat is the sentence that is correct. The cat sat is the correct sentence. The cat sat on a is the correct sentence. It's not the cat sat pad on. So that's why what you do is that you prefix it with all the pads and then you put the available tokens towards the end to fill up that max sentence length, and then you pass that as an input. Okay. This is the code that does that. It essentially tokenizes, then it creates things of that sequence length, then it pads it appropriately, and it pads it by putting it in the beginning. Okay. And by the way, there's another thing called you know when you do something like this, sequence to process the keras.preprocessing.sequence.pad sequences. What it also does is that it also, automatically, instead of passing words or text, it will substitute those words or those, tokens with the index of that word in the vocabulary. That's what you see here. Okay. The, let us say, is 1, and that's why it's here. Cat is 2, so that's why it's here. The is 1, so it's here. Cat is 2, it's here. Sat is 8, and so on. That's what it's doing here. Okay. By the way, this is a continuation table. It's not 2 tables. It's one table that is wrapped around like this. Okay, with this out of the way, let's go back and look at our collab notebook and build something where you want the RNN to predict the next words. Okay, here is my collab notebook. What I'm doing is I'm going to be importing some libraries. I'm saying that my maximum sentence length is 10. I'll use a word embedding size of 300. Remember that neural networks do not understand numbers. Sorry, do not understand words. So you have to pass numbers. So I'm going to use embeddings, and I'm going to use 300 dimensioned embeddings. Okay. This code I've already shown you. All it does is a routine that helps you take a sentence and it tokenizes everything. Okay. So we don't really have to look at this code. You're more focused on how the training happens and how it infers. Okay, so I've used about, let's see how many, about 50 training sentences, and I want to train my neural network on those 50 training sentences. So that's my 50 training sentences. And by the way, when I take the 50 training sentences and I tokenize them and I pad them, this is how it looks. All right, this is how it looks. Okay, there's the one hot encoding for the predicted next word, by the way. Okay, and this is the IDs for the token IDs from the vocabulary that represents that word. Okay, now with this, let's go and see how we train this neural network. Okay, let's go here. By the way, from the internet, I have downloaded the GLOW embedding as well as word-to-vec embedding, and we can use either of them for converting our text to word embedding so that we can pass it to the neural network. Okay. If you do not know what a word embedding is and why we are using it, I would very strongly encourage you to see episode 2 of season 2 called Word Embeddings, and I actually go through a lot of details as to what they are, why they are used, what is the intuition behind it, and I show you some really cool demos with that too. Okay. All right, so I'm going to skip this part of the code because, again, I explained this in season 2, episode 2. You're essentially creating an embedding matrix here from the global embedding matrix. This embedding matrix is a subset based on just the tokens that appear in your training data. Okay, why we do that, I explained that in season 2, episode 2, so you can go and see it there. It's not relevant to this discussion, so I'm going to skip it. But just suffice it to say that, okay, this is where I am having my embedding matrix being built from the global embedding matrix that I've downloaded from the internet. Embedding matrix is specific to the training data that I have. Okay. Now I'm going to let me build this. Okay. I'm building a recurrent neural network. I show you two models. One is if I'm using pre-trained embeddings, which I show you here. And then other one is, if I'm not using a pre-trained embeddings, what you're doing here is that you are essentially also training the embeddings alongside training the recurrent neural networks, to make the right prediction. Both those models work, by the way. And the way you do that is, okay, the first layer is going to be the embedding layer. We studied that in season 2, episode 2. Then I create a recurrent neural network. I'm creating a 100 cross 100 or 100 by 100 matrix for my context. Same thing here, you can see here. Okay. And by the way, the only difference between these two is that in the first case, I'm using a pre-trained embedding. And the second case, I'm actually training the embedding matrix also along with the recurrent neural network. Then I compile the network and I use Adam optimizer, and I'm using cross entropy because why I'm predicting the next word, which means that I'm going to be using softmax as my output function. We studied this both in episode 2 of season 2 as well as episode 2 of season 1, why softmax is used and why cross entropy is the corresponding loss function. You can refresh your memory by going to both those episodes. Episode 2 of both season 1 and season 2 capture this information. Okay, then I train my neural network. Let's train it. Okay, I'm training it across 100 epochs. I'm doing it with batch size of 32. Okay, so you can see the loss starts pretty high and it is going down. The accuracy of predictions is increasing. Let's go through the 100 epochs. Okay, there you go. The loss is still not very low. Typically, the loss has to be pretty low for most accurate predictions. It has to be like 0.00001 or something like that. But that's good. I mean, we are trying to demonstrate the use of recurrent neural networks rather than building out something that is meant for production use. So this is good. I mean, I think our prediction accuracy should be about 88%, which is good enough for appreciating what the RNN does here. Okay. All right. Now let's go and predict the next token. And I wrote some code here that does essentially the same thing. It basically takes the first set of words that you give it, which is the prompt. Let's say this is the prompt. I drink coffee, and you wanted to predict what comes after that. How many words you wanted to predict? You wanted to predict three words after what comes after I drink coffee. So the first thing is that you need to tokenize that I drink coffee. It tokenizes into three tokens. Then what you do is that you again do the padding like we saw with the training. Then you pass it through the predictor. It predicts the next token, and then you convert that token back into the corresponding word from the using the vocabulary, and then you append it to the text. Okay, append it to the text, and then you pass that back because you're predicting the next three tokens, not just the one token, right? So essentially, the first thing it goes is I drink coffee and whatever the predicted token. The next run is I drink coffee and with the predicted token to get the next one. Then the same, this goes in a loop. So that's what you do here. So okay, let me run this. Let's see what happens. So it said when I gave it I drink coffee, it predicted with milk and I put the predicted words in bold so you can see it very clearly. I think it's a pretty darn good prediction. I drink coffee with milk and. Very good. The sun rises, that's what I gave it, and it says in the east. It's a very good prediction. John goes to the gym every. I'm pretty sure if I give four, maybe it'll predict every day. Let's see, I want to predict the next four words. Let's see what it does. Yeah, every Monday. Yeah, that's pretty good. So, as you can see, right, I think even with an accuracy of 88%, and even though the loss is not completely converged, I think our neural network is able to predict the next tokens very nicely, right? So, so that is what a recurrent neural network does. And I think it's a very powerful neural network architecture that allows us to take data that your feed forward network is not able to process because it does not understand the context that is flowing across a single input. The input could be a sentence as an example, right? Or a time series window as an example. A feed forward network has no way to capture that context. A recurrent neural network has that way to do it. And what we have seen is that you can use this architecture to process things like predicting next words in sentences, processing time series data to predict what is going to happen after the current window for which you have the times the data and so on. So it's a very powerful architecture. With that, we conclude this episode. In the next episode, we are going to look at an optimization to the recurrent neural network called long short term memory, LSTM, which is a very popular way in which you can do sentence predictions or next token predictions and so on. And I'm going to teach you LSTM with a lot of intuitive examples, so do not miss that. And until then, happy learning. If you like this video, please like it, subscribe, and share it with other people as well. Thank you.